So in the last video, we talked about how this propyl group could have different modes of attachment to other parent chains. So we said that we can have this propyl group or we can have an isopropyl group. We also talked about the butyl group. So this would be the butyl group, meth-eth-prop-but. And we said that the butyl group could have this kind of attachment where this last carbon right here could be attached to the parent, or we could have the tert-butyl attachment. And this is basically where we have the same number of atoms, meth, eth, prop, but, but we have them attached in a slightly different way. So again, this kind of looks like a linear chain, and this kind of has one of the crow's foot configuration. There are actually a couple of different ways, other ways that you can attach a butyl group to a parent, and those ways are shown right here. So this has its own name as well. This is called a sec-butyl group, and this group is called an isobutyl group. And again, this is just a regular butyl, and this is a tert-butyl. So what's interesting about these butyl isomers is that the only difference between the two between the four, is that they only differ in the way that the atoms are connected to each other. Every single one of these different ways of arranging the carbons are, they're all different, but they have the same number of carbons: 1, 2, 3, 4, 1, 2, 3, 4, 3, 4, 3, and 4. So again, the only difference is that they change in the way that they are connected to each other. These types of branches would be referred to as constitutional isomers because they differ in the way that the atoms are connected to each other. Another example of a constitutional isomer pair would be these two molecules. Notice that while these two molecules have the same number of carbons and the same number of hydrogens, these two methyl groups are attached to different positions overall on the cyclic ring. And so because of this, these two molecules would be referred to as constitutional isomers. We could also have a different type of isomer pair where these two molecules don't differ in the connection points between the atoms, but they do differ in the three-dimensional orientation of the attachments. So this would be an example of that. Before we move on, it's worth it to point out the nature of this wedge kind of structure versus this dash kind of structure. So these are actually telling you a little bit of information, and this wedge is really telling you that that this molecule isn't really flat, it's in 3 dimensions. And so what it's telling you is that from your perspective, this methyl group is kind of pointing towards your face, like you put on a pair of 3D glasses. And so just like if you put on a pair of 3D glasses and this methyl group is pointing towards you, this methyl group is actually pointing away from you. So it's pointing kind of into the other room. So you have to kind of pretend that you're able to see in 3 dimensions, even though you're really looking at the computer screen. So if you compare these two molecules right here, these molecules aren't really differing by the connections that they have. So if it was a constitutional isomer pair, they would have to differ by how the methyl groups were attached. But those really haven't changed. If this is carbon 1 and this is carbon 2, the two methyl groups are still attached by position 1 and position 2. What has changed is the way that these groups are oriented in space. So if both of these are pointing at you with your 3D glasses, one of them is now pointing towards you and one of them is pointing away from you. And we would call these two molecules not constitutional isomers anymore, but stereoisomers. And these molecules are isomers that differ only in the way that the atoms are oriented in space.